Well, howdy everybody, and today we want to do a real quick review of saturated solutions, and really we want to focus on KSP. But to start, let's just talk very quickly about a saturated solution. What is a saturated solution? That is an equilibrium between dissolved and undissolved solute. Good. And the important thing here is just an equilibrium. Now let's take something that we know. How about something like calcium fluoride? And it is a saturated solution, right? That means it's a precipitate. And what will that be? That will form a equilibrium between dissolved solute and undissolved solute, right? Here is my undissolved solute, and here is my dissolved solute, and so it would look like this. This is the way this is an equation for a saturated solution, right? And how would I know it's saturated? Well, there would be a test tube, and I'd have some solid calcium fluoride, right, in a solution. If it's solid, that means I've got an equilibrium between dissolved and undissolved. So there you go. That is what we would see. And anytime you have a precipitate, you have a saturated solution. Now, KSP, since this is an equilibrium, it has a K, we call this the solubility product constant, and the KSP is calculated the same way as any other K, or equilibrium constant, and that means we only worry about the aqueous and the gases, in this case aqueous. So my KSP for my calcium fluoride is equal to the concentration of my calcium times the concentration of my fluoride squared. There we go. Now, one thing about KSPs is this idea of solubility. What is solubility? Hey, that is the amount of my solute which dissolves, right? This is the amount of solute dissolved at equilibrium, right? When we're at our equilibrium. Good. Now, how do I figure out solubility? By the way, this is usually in grams per liter or grams per milliliter, something like that, moles per milliliter of my solvent and solute and solvent. Good. Let's talk about some calculations here. How do I determine the solubility given a KSP? Okay, so let's take a look at what we had up here. We had my calcium fluoride, and it has a KSP of 3.9 times 10 to the minus 11. So KSP equals 3.9 times 10 to the minus 11. And we want to calculate this solubility. Now, let me tell you, it's really pretty easy. We're going to make an ice box. Okay, and you guys should be experts at ice boxes. And since this is solid, we really don't care. We have 0, 0 at the beginning. This would be minus x, this would be plus x, and this would be plus 2x. Since this is a solid, we don't care about that. This is x, and this is 2x. Now, here's the thing. See this x right here, this minus x? That is my solubility. The amount of my my calcium fluoride, which dissolved, which is this x, is equal to my solubility. So when I'm calculating solubility, I'm really trying to get x. Good. Well, we have our KSP, and the expression for that would be my calcium, right, times my fluoride squared. So I would substitute. So let's drop in my numbers. I have an x here for my calcium. I have a 2x for my fluoride. And what do I have to do with that 2x? I have to square it. And I know what my KSP is, so I can say that 3.9 times 10 to the minus 11 is equal to x times, what is 2x squared? 4x, which would mean 4x cubed is equal to 3.9 times 10 to the minus 11th. Solve for x, and that is your solubility. We're not going to run the numbers because we want to save time, but that's how you would do this. Now, how do I get KSP given solubility? Okay, let's take something that's maybe a little easier. How about, let's take my, I don't know if it's any easier, how about my silver chromate? Let's take silver chromate. And so what's it going to do? We're going to have silver chromate solid is going to break into 2 silvers, right? Aqueous plus 1 chromate aqueous. Good. And we do our ice thing, ICE, and I'm given a solubility. So there, for instance, we'll say that my concentration of silver at equilibrium is equal to, how about 1.3 times 10 to the fourth? 1.3 times 10 to the fourth molar. So they have to give me something like this, right? So we're going to do my ice thing. I don't care here, minus x. I don't care here. This is going to be nothing to begin with. This is a plus 2x, and this is plus x. Why is that? Because I have a 2 here and a 1 there. So this is a 2x, and this is an x. And when I write my expression, KSP is equal to what? Okay, I always like to write these out first before I substitute. Silver squared times my chromate, right? There we go. And then we're going to substitute here. So this be, here's my silver, so 2x, and I have to square it. And here's my x. So my KSP is equal to what? 4x cubed. However, what do I know? I know that my silver concentration is equal to 1.3 times 10 to the minus fourth. So what is that? So I have my silver concentration is equal to 1.3 times 10 to the minus fourth, but that is also equal to what? 2x. 2x. So then I can solve for x. X is equal to 1.3 times 10 to the minus fourth over 2. And then what am I going to do? I'm going to substitute in here. And when I substitute in there, I can run my calculator and solve for KSP. That's the way you do that. Okay, moving on. Here we go. Factors which affect solubility. I'm going to need some space here. Sorry. I'm going to have to yoink, erase my beautiful last calculation. Now, common ion. Let's go back to our initial question. Calcium fluoride, right? Solid goes to calcium plus 2 fluorides, and these are both dissolved. They're aqueous. Good. Now, let's say that this is in a 0.1 molar solution of NaF. So instead of being in water, we're going to drop this stuff in sodium fluoride. And the question is, what effect would that have on solubility? Now, there's a qualitative and a quantitative way to look at this. What am I doing here? This is going to break into, since it's a strong electrolyte, sodium ions and fluoride ions, right? So that means that's at the beginning. That means, what am I going to do? I am going to increase my concentration of my fluoride. Well, what's that going to do to my equilibrium? What's going to shift my equilibrium this direction? And if it shifts that direction, that means I'm going to have less of my aqueous in solution. If it's less, that means my solubility is going to do what? My solubility is going to decrease. That's the way you can think of this qualitatively. Now, the other way is I can remove fluoride, and if I remove fluoride, then my concentration is going to go down, and it'll shift my reaction this way. And if that happens, then my solubility is going to go up. Good. By the way, how could I remove fluoride from the solution? Well, what do we know reacts with fluoride? How about H plus, right? Because H plus F minus is going to form our HF. So that would pull fluoride out of solution by putting it in what? An acidic solution. So for instance, if I drop my pH, I'm going to increase my concentration of H plus, which will then react with F minus, which will cause my F minus concentration to decrease, which will cause my equilibrium to shift in that direction, and my solubility will go up. Ooh, mama. Okay, let's try to talk about this with some numbers. Let's talk about this quantitatively. All right, so let's go back to our calcium fluoride. Going to calcium 2 plus 2 fluorides, right? And I know I'm going fast, but I'm assuming this is a review for everyone. And I have sodium fluoride 0.1 molar. Good. And we're going to do our ice chart. ICE, yoink, minus X, yoink, 0. But notice, I don't start off now initially with 0 for fluoride. What do I start off with fluoride? I have 0.1 molar fluoride. So this is now a minus X, or excuse me, a plus X. This is a plus 2X. Good. And then what do I have down here? X. and this is going to be 2x plus 0.1. And now let's write my expression for my KSP. My KSP is equal to the concentration of my calcium times the concentration of my fluoride squared. My KSP, what was my KSP up here? About 3.9 times 10 to the minus 11th. So 3.9 times 10 to the minus 11th is equal to, what's my calcium concentration? X. What is my fluoride concentration? 2x plus 0.1, and I'm going to square that. And if I were to solve that, that would require a quadratic. Yuck. So what are we going to assume? We're going to assume that x is much, much smaller than 0.1. And when we do that, I get 3.9 times 10 to the minus 11th is equal to x times, now my 2x. If x is much, much smaller, my 2x is essentially 0. So I have my 0.1 squared. There we go. And I solve for my x. And my x will be my concentration of my calcium, but it is also what? It is also my solubility. There you go. So that's how you do that quantitatively. Another thing that we can do that would have an impact would be changing the pH. We showed you how changing the pH could affect fluoride. Let me show you another one that's a little more interesting. Let's take something like magnesium hydroxide, manganese 2 hydroxide. So let's take manganese 2 hydroxide. That's solid, right? And it's going to go to manganese 2, aqueous, plus 2 hydroxides, right? That's it's a saturated solution. Good. And let's say that this is not at water, but this is at a pH of 10, which means it is basic, right? Now, quantitatively or qualitatively, we can figure what happens. If my pH, why did I say 4? pH equals 10. If my pH goes up from 7, what has happened? That means my hydroxide concentration has increased. So this goes up. What's my equilibrium going to do? My equilibrium is going to shift back toward my reactants, meaning less of my solid manganese hydroxide will dissolve and my solubility goes down. So that is qualitatively what happens. Now, let's talk about a quantitative approach to this. Here's the big difference. Remember in the last one when I gave you, in this last one I said you had 0.1 molar NaF, and they said, hey, that is a initial concentration for my fluoride. When they give you this pH, they are giving you an equilibrium concentration. So what am I going to do here? I'm going to look at pH and say that, hey, my POH is equal to 14 minus 10, so my pH is 4, which means my concentration of my hydroxide is 1 times 10 to the minus 4th, and that is an equilibrium concentration. So let's run our icebox. Here's my ICE, don't care, minus X, don't care. This is X, oh no, it's not. It's 0, and this is 0. This is plus X, this is plus 2X. So this is X, and this is plus 2X. But what do we know? Well, first, let's write our expression. My expression for KSP is equal to my manganese 2 times my hydroxide squared. And what is that equal to? Well, that's equal to X times my 2X. And my 2x has to be squared. But what do we know here? These guys are equal. So that means 1 times 10 to the minus 14th is going to go where? 1 times 10 to the minus 14th is going to go right in here. And we're not going to put the 2x. We're going to put the 1 times 10 to the minus 14th. My KSP, by the way, I know my KSP. My KSP is 1.6 times 10 to the 13th. 1.6 times 10 to the minus 13th. Now remember, I don't solve for x here. Why not? Because I'm not going to solve my x here. I'm going to solve my x here, okay? And I know that might be a little confusing. Let's restate that. I have 1.6 times 10 to the minus 13th is equal to my X times my hydroxide concentration squared. Got it? We're not going to put in the 2x here. We're going to put this. I already know that this is equal to 1 times 10 to the minus 4th. So I have 1.6 times 10 to the minus 13th is equal to x times 1 times 10 to the minus 4th squared. And I'm going to solve for x, and that'll give me my solubility. All right? Good. I hope that's making some sense. One other big thing that we're going to focus on are complexing agents. So let's go with something that we know pretty well. Silver chloride solid is going to silver plus chloride minus, right? There we go. And complexes are things that form between Lewis bases and D block, mainly D block cations. Got it? Which are acting as Lewis acids. And what are my typical Lewis bases? Things like ammonia, things like hydroxide, cyanide, thiocyanide. Those things are all going to, when you see those things are all going to be, keep your ears open for those because you may be having a complex issue. So let's say we have 0.1 sodium cyanide in, so my silver chloride is in 1.0 molar sodium cyanide instead of in water. What's going to happen? Well, my silver is going to form a complex. My Ag plus is going to react with 2 cyanides to form the complex, which is AgCN2 minus, right? And it's not so important that you know this because I mean, I don't think they're going to really ask you a quantitative question. What's the important thing to understand is this silver is going to react with the cyanide. So what's going to happen to the concentration of this silver? The concentration of the silver is going to go down. So how is the equilibrium going to react? The equilibrium is going to shift in that direction, and when it does, that means more of this goes into solution, meaning my solubility is going to go up. So when I add a complexing agent, my solubility is going to increase. Great. And then temp, just remember, we have to decide is it exothermic or endothermic, right? And depending on which that is, if I increase my temp, it's going to shift it one way or the other. We know that from our last discussion of equilibrium. And just remember, you know, we can think of endo as a reactant and exo, heat as a product. So if I have an exothermic reaction where, let's see, we have Yx going to X plus, I don't think it's X, Y plus X minus, and it's exothermic, that means heat is over here. So if I increase heat, my reaction is going to shift in that direction, meaning more of my solute is going to stay undissolved, meaning my solubility will do what? Go down. Got it. Finally, let's talk about predicting precipitation. This is pretty simple. We're going to use Q, and we're going to compare it to what? K, right? And remember, so here, let's go back with my silver chloride, and here's my solid. So it's Ag plus Cl minus aqueous, right? And aqueous. So my Q would be what? Concentration of my silver times the concentration of my chloride, whatever they are. My K would be concentration of my silver at equilibrium and concentration of my chloride at equilibrium, right? So then I compare those two. If Q equals K, then we are at equilibrium. If Q is greater than K, then we will precipitate until what? Until Q equals K. And if Q is less than K, then you are unsaturated. Good. Final one. Let's say we want to know what's going to precipitate first. Let's say I have lead 2 chloride and I have silver chloride. And we're going to start adding some chloride and see which one of these precipitates first. And let's say, let me see, we do need some initial concentrations. How about 1 times 10 to the minus 2? So I have 1 times 10 to the minus 2, 1 times 10 to the minus 2 is my concentration of my silver. And 2 times 10 to the minus 2, 2 times 10 to the minus 2 is equal to the concentration of my lead 2. And we're going to start adding chloride, and which of these is going to precipitate first. So what we're going to do is what? We're going to write the KSPs. We need to know some KSPs. My KSP for lead chloride is lead 2 chloride is 1.7 times 10 to the minus fifth, 1.7 times 10 to the minus fifth. And my KSP for my silver chloride is 1.8 times 10 to the minus 10th, 1.8 times 10 to the minus 10th. Good. So then we're going to set these up. We'll write this expression. This is equal to the concentration of lead 2 times the concentration of my chloride squared. This is equal to the concentration of my silver times the concentration of my chloride, right? But what do we know? I know the concentration of my silver, and I know the concentration of my lead 2. So 1.7 times 10 to the minus fifth is equal to 2 times 10 to the minus 2 times the concentration of my chloride squared. Over here, I have 1.8 times 10 to the minus 10th is equal 1 times 10 to the minus 2 times the concentration of my chloride. Good. What do? Solve for chloride here, solve for chloride here. Whichever is the smaller amount will precipitate first. Got it? Whichever amount of chloride is less, the lesser amount of chloride will cause precipitation first. Got it? So if this is the lesser amount, then my silver chloride precipitates first. If this is the lesser amount, then my lead 2 chloride precipitates first. Got it? All right, that's about it. I hope you understand. Good luck on the test in, 2 weeks. Bye.